ये लेक्चर नंबर 5 है. Hello everyone, welcome back. Today we are going to start discussions on compressible flows. So basically in CFD, as we know, it is very important to know what are the correct governing equations to get the correct solutions. Okay. So for that we will first try to understand how the compressible flows are different from incompressible flows, because the equations are different for the compressible flow and incompressible flow. You might be many of you have done CFD, you would know that let us say if the fluid involved is liquid, okay, then you can do away with your incompressible solver, but if the fluid involved is the air, okay, and then you would require basically a compressible solver depending on what is the speed of the flow, right. So, if the speed of flow is higher, let us say above a certain Mach number, and we will come to what is Mach number, okay, then you have to use a compressible solver, okay. Then you can have problems which involve shocks, right. So, in those kind of problems we need to have a compressible solver. So, in this class we try to find out how the compressible flows are different from incompressible flow. So, we will go back to very basic theory which we might have studied long back, okay, during our high school, okay. So, we have got solid, liquid and gas, and liquid and gas together are called fluid, okay. So, when we say compressible fluid dynamics, so we try to solve the dynamics for both liquid as well as gases, okay. So, how these liquids and gases are different from solids, okay. So, as you can see here, if you let us say a box, okay, and you put a solid blob there, okay, solid block there, okay, you would see that the block holds shape, okay, in the container, and it has got a fixed volume, okay. Now, in the same container you remove the block, okay, and then you put let us say water, right. So, the water will quickly take the shape of the container, right, and what is the other advantage, the other property is that it will have a free surface, okay, and it will still have the fixed volume, okay, right, because depending on how many liters of liquid that you are putting, it will maintain the same volume there, okay. So, the main difference between the solid and the liquid is that in the liquid it takes the shape of the container, it does not hold the shape, and it also has the free surface. Now, between the liquid and gas, okay, now in the same container if you put gas particles, what will happen, it will take the entire volume of the container, right, and it will not have the free surface, it will take the shape of the container and it will still take the volume of the container, right. So, this liquid and gas, okay, because they both take the shape of the container, basically they flow, okay, and that is why they are called fluid. So, fluid is what flows or what can flow, okay, and solid is what is rigid, okay, it cannot flow. So, that is the one of the major difference between the solid and the fluid, okay. So, the fluid flows and solid are rigid, okay. Now, in terms of forces for interaction, okay, in the case of solid, the molecules are very closely packed, okay. So, the forces of interactions are high, okay, and yeah, there is an error here, okay, the intermolecular distance will be low and high in the case of fluid. Okay, so the force of attraction will be high in the case of solid, precisely because the intermolecular distance is low, okay. In the case of solid, the moleculars are very closely packed, as you can see in the last diagram here, you can't even identify the molecules, but if you could see it, okay, they are very closely packed, okay, they are slightly sparsely packed here, and here you can see that they are very sparsely packed in the case of gases, okay. So, solids have high forces of attraction, and fluid have low forces of attraction. Okay. One of the major difference between the solid and the fluid in terms of our discussion for CFD is how the stress vary. Okay. In the case of solid, the stress is proportional to strain, okay, and the proportionality is the Young's modulus, as you all know, right. So, if you apply some stress, okay, some force, there will be some deformation and the stress will be proportional to the strain. In the case of fluid, that is not true, okay, and that is how the fluid differ from solid. Okay. When I say fluid, I mean both the liquid as well as the gas. Okay. So, in the case of fluid, if you apply stress, if you apply force, okay, the strain will happen, but the stress tau will be not proportional to the strain, but the strain rate. Okay. Tau will be basically proportional to some strain rate. Okay. So, U is basically meter per second. So, this is basically an indication of the strain. Okay, is the change, is the displacement per unit time, right? That is U. Okay, and the rate at which the U is changing, the du by dy, it can be du by dx also. Okay, so the tau is proportional to the strain rate. Okay, and what is the proportionality of constant? You have all read in your basic fluid mechanics about the Newton's law of viscosity. Okay, and the proportionality of constant will be the viscosity, right. So, this one major difference you must remember, that in the case of solid, the stress is proportional to the strain. In the case of fluid, the stress is proportional to the strain rate. Okay. Now, we will see the difference between the liquid and gas. After understanding how the fluids are different from the solids, let us look at how within fluids, what are the properties in which the gases differ from the liquids. Okay. So, one difference that we saw is that the liquid basically have the free surface and gas basically fills the container. Okay. So, that is one difference we already saw. Okay. Let us talk about the mean free path. Okay. What is mean free path? It is a kind of a measure of intermolecular distance. It is like how much one particle moves before it collides with another particle. So, you have a, let us say you have a container, okay, and you have these particles present here, okay, and they keep on moving. Okay. So, how much they travel before they collide to the next particle is your that the average distance of that is called the mean free path. Okay. It is usually denoted by lambda. Okay. So, the mean free path is low in the case of liquid. Why? Because the molecules are closely packed, right. So, it will compared to gas, it can easily collide with another molecule. Okay. The compressibility for the same region, and we will go through the formal definition of the compressibility in a few slides. Okay. So, in the case of liquid, the compressibility is very low, it is of the order of 10 to the power minus 10. Okay. So, what do you mean is that if you press it, okay, the amount of volume that changes due to the pressure is much lower in the case of liquid than the gas. Okay. So, in the gas, the order of the compressibility is 10 to the power minus 5. Okay. Typically, because the compressibility is very small, very low in liquid, okay, the equations that we employ is the incompressible Navier-Stokes equation. This is incompressible. See, remember one thing, there is no fluid which is truly incompressible in nature. Okay, whenever you apply a force, okay, it will change the density. Okay, but the change in density is very low, and so much low that you can ignore it for all practical purpose in basically getting the essential dynamics that you want. Okay. And when you ignore the change in density, basically the things become simpler, and that is why we go for the incompressible Navier-Stokes equation. Okay. In the case of gas, we do not have that luxury, especially if the speed is higher than certain value. okay, and then in those cases we have to go for the compressible Navier-Stokes. Okay. Now, for the next few slides, we will have discussion about the gases only, okay, and why is that is because we saw that the gases are compressible, okay, and they can basically the particles or molecules interact very easily, okay, but they have the intermolecular forces weaker than that we have in the case of liquid, and in the liquid it is weaker than that we have in the solid. So, we can make several approximations and we can work in a perfect or ideal gas scenario where the things becomes much simple. Okay. So, what is the perfect or an ideal gas? Okay. It is the gas where the intermolecular forces are neglected, okay, and the gas is not chemically reacting. Okay. So, we have intermolecular forces, but at certain temperature and pressure, let us say a typical temperature of your room condition or the pressure of the room condition, let us say around 273 degree Kelvin, okay, and pressure of around 1 atmosphere, okay. The intermolecular forces are not that important, okay, and then the gases will not react also because the temperature is not that high. So, we are talking about temperature around let us say 273 to around 1000, okay, and the pressure around at 1 atmosphere. In those cases we can ignore the intermolecular forces, okay, and we can use the ideal gas equation. Now, the ideal gas can be of two type, okay, one is the calorically perfect gas, another is the thermally perfect gas, okay. So, what is calorically perfect and thermally perfect? So, if you have a gas, we will have this internal energy E, okay. Now, this E can be a function of both the temperature and volume or temperature and pressure, okay. So, here V, okay, I am writing V like this. So, V is the specific volume, which is basically the inverse of your density, which is volume per unit mass, okay. You might have read about the extrinsic properties and intrinsic properties, okay. So, we are dividing the volume per unit mass so that we can talk about the specific volume. Now, the change in internal energy of a gas can depend both on the temperature as well as your pressure, and because this pressure, temperature and volume are related, we can also say temperature and the specific volume. So, if the internal energy change depends on both the temperature and the specific volume, then it is called the real gas, okay. But if you can ignore the intermolecular forces, then what happens that you can claim that my change in internal energy only depends on the temperature and not the specific volume, okay. So, your E becomes E of T, okay. Now, this is your thermally perfect gas, okay, where you are ignoring the change in internal energy or even enthalpy. You can talk about enthalpy also. So, what is enthalpy? Is H equal to E plus P by rho. Okay. So, because we are discussing everything in terms of your the per unit volume property, okay. So, both E and H depends only on temperature, okay. Now, if we can make even more approximation, and so we can say that okay, there is a constant which can determine how the internal energy or Cp is changing with temperature, okay. So, in this particular case we can write dE equal to Cv dt, okay, and dH equal to Cp dt. Where you have read that Cv is the specific volume at constant volume, okay, specific heat constant at constant volume. So, that will be dE by dt at volume, constant volume, and Cp is equal to dH by dt at constant dH by dt at constant pressure. So, you can write your dE and dH in terms of this, okay, and that is true in general for a thermally perfect gas, right. So, if you can make another approximation where we say that my Cp and Cv are basically constant, okay, in that particular case you can further approximate it and you can say it that E is equal to Cvt and H equal to Cpt, right, where what we did was we just did the integration here, took the Cp Cv out because they are constant, and we say that my internal energy is 0 at T equal to 0 and H is equal to 0 at T equal to 0, and you can get this expression, okay. And these are basically true if the temperature is less than 1000 Kelvin, okay. Then in this case, if the temperature is less than 1000 Kelvin, then your Cp Cv does not vary too much with temperature, and you can assume to it to be constant, and these are called the calorically perfect gas, okay. Okay, so this is what is written here. You have the calorically perfect gas where E equal to T less than 1000 Kelvin, but if the T is more than 1000 and less than 2500, then it is called the thermally perfect gas. In that case, we cannot assume Cp and Cv to be constant, and you can use this E equal to Et, but you have to use the integral quantity. Okay, now let us go to the real gases. Okay. So, there are two extremes here in the real gas. Okay, so real gases, the intermolecular forces are important. Okay, your both E and H will be basically a function of temperature and volume. Okay, H equal to H dV. Okay, so this is true at very low temperature. Let us say less than 250 Kelvin and high pressure. In those cases, the molecules are very close and the intermolecular forces are important, and we cannot use our perfect gas law here. Okay, we have to use this van der Waals gas law, or there are some other laws also. Okay, in the case of calorically perfect gas, we can use this ideal gas law or perfect gas law, which is basically P equal to, or let us say PV equal to nRT. Okay, this law can be used. In the case of real gas, okay, we cannot use that law and we have to go for more complicated laws like van der Waals gas law. What happens when your gas is chemically reacting? That means, if your temperature is more than 2500 Kelvin. Okay, in that case, what will happen that you will have continuous conversion from one gas to another gas. Okay, and in those cases, your R that you have written here, the gas constant will basically vary. Okay, so it is not equal to constant. Okay, R varies because you have continuous conversion from one gas to another gas, and that is why we cannot use this approximation of ideal gas law or even the thermally perfect. Okay, so you have to consider this as a chemically reacting gas. Okay, so this is true for the gases. So typically, if you see many of the CFD simulation that are performed, they are into this condition, they fall into the condition of normal temperature and normal pressure. Okay, of course, there are extremes where you cannot use this. So in that case, you can use this P equal to rho RT or PV equal to nRT. Okay, you can use the ideal gas law. Now, what about liquids? Okay, so liquids also have equations of state, but they are much more complex. Okay, so for all practical purpose, what we can do, the equation of state as volume is constant, that volume is not changing. Okay, so that means that pressure work is negligible in liquids compared to gases. Okay, so we do not require a separate equation of state. Okay, because we say that our volume is not changing or our density is not changing. Okay, now go to the perfect gas. Okay, so the perfect gas, as you might have read, the expression is PV equal to nR, and I am using the symbol Ru. Okay, why? The Ru I am calling it as a universal gas constant, and what is the value of Ru? Is equal to 8.314 joule per mole Kelvin. Okay. Now, when we do CFD simulation, we want to basically use the value in terms of per kg instead of per mole. Okay. So, what we will do, we will convert it to in terms of per kg. Okay. So, you can divide it by the molecular mass, this will become P V by m is equal to R u by m by n multiply by T. Okay. This is volume per unit mass, that is nothing but P by rho, that is inverse of density, right, mass per unit volume is density. Okay. And this quantity R u by m by n, okay, this is your universal gas constant divided by your molar mass, right. So, this constant can be written as the specific gas constant R and then multiply by T, right. So, then you will get a quantity which is P equal to rho R T, okay, which is used in your CFD simulation with ideal gas assumption, right. So, here R is nothing but R u, which is the universal quantity, universal gas constant divided by m by n, which is your molar mass, right. Now, unit of this will be R will be because this is joule per mole Kelvin and this is kg per mole. So, this will become joule per kg Kelvin. Okay. Now, one thing very important to remember here is that R u is the universal value, but R will change based on the gas that you are using because the molecular mass of gases will be different. So, for example, what is the value of R for air? Okay. So, if you assume that okay, air has got let us say around 79% nitrogen and 20% 1% of oxygen, okay, and this has got nitrogen has molecular mass of 28, oxygen has got a molecular mass of 32. Okay. So, then the molecular mass of the air will be around somewhere like 29. Okay. And if you want to calculate R will be okay 8.314 and this is in gram. Okay. So, this will become by 29 into 10 to the power minus 3, okay, and that will become around 287 joule per kg Kelvin, and this is the value that you typically use when you simulate a ideal gas. Okay. You can calculate, let us say now you change your medium in your simulation from the ideal gas to nitrogen. So, then all you need to do is that divide this 8.314 divided by 28 and you will get the new gas constant. Let us say you change it to helium, divide by the molecular mass of the helium and you will get a much higher value of your gas constant, okay, specific gas constant. So, that is why this R is called the specific gas constant. Okay. So, this is important to remember. The two take away from this slides, that we want our R in the unit of joule per kg Kelvin in our CFD simulation, and for that we will basically divide the universal gas constant with the molar mass. Now, come to the property of the compressibility. Okay. So, as we have been discussing, so let us say if you have a gas or liquid, any fluid in a container, and if you apply pressure, okay, so the volume will change, okay, and the volume may also change if you heat it up. Okay, let us say you are heating it up, then also volume is changing, right. So, the volume can change due to the temperature and due to the pressure. So, the V is now V T comma P. So, you can write it as del dV, okay, is del V by del T dt plus del V by del P dP. Okay. So, we will call our fluid to be compressible if the change in volume, there is a great change in volume due to the application of pressure, okay, and we will the change in volume due to the temperature is not considered as a property of the as the compressibility property of the fluid. Okay. So, we will define our compressibility tau is equal to minus 1 by P. Why there is a minus sign? Because when you are applying the pressure, your volume is shrinking. right. So, that will be negative del V by del P, or you can write it minus del V by V divided by delta P, right. So, basically the change in your specific volume per unit volume due to application of pressure, right. So, that is what your compressibility. Now, if you change the pressure, not only the volume changes, but also the temperature changes, right. Let us say you fill in air through a pump in your bicycle, you would see that it becomes warmer, right. The tire becomes hotter, right. So, your temperature will increase when you apply the pressure, but if there is a mechanism through which we can keep the temperature constant, okay, by doing some heat transfer and so on, then that is called the isothermal compressibility, tau T. Okay. So, where we are seeing that it is constant it is done at the constant temperature. The change in volume occurred due to the change in pressure at a constant temperature. And if we can do it isentropically, okay, basically very slow process, okay, and then it is called the isentropic compressibility. That means the entropy is constant while the volume is changing due to the application of pressure, right. Now, let us calculate the value of compression. Now, before we go there, so we can also write it, because tau is okay minus 1 by V dV by dP, and since V is equal to 1 by rho, this can be written as tau equal to 1 by rho d rho by dP. Now, there is one interesting thing you can see here is basically d rho is equal to rho tau dP, right. So, this tau compressibility is basically the property of the fluid, okay. And so, if the tau value is less, okay, if the tau is very small, okay, even if you apply the pressure, okay, a great deal, your change in d rho will be very small. As we discussed, for the liquid the tau is around 10 power minus 10, okay. So, when you apply I mean very high pressure, the change in density may be very small, and if the change in density is less than 5%, then we consider that to be basically an incompressible fluid, okay. If the change in density is greater than 5%, then only we need to treat it as a compressible fluid. So, here the tau is very important factor, because that determines how much the density will be changing due to the application of a pressure. So, compressibility is the property of the fluid. Now, let us calculate the isothermal compressibility of fluid, and then we can I mean conclude the class today, okay. So, you have this we are trying to calculate it for air. So, we can use our ideal gas equation, because it is done at 1 atmosphere. So, ideal gas equation is P V equal to R T, right. So, the V will become R T by P, right. And for compressibility, what do we want? Del V by del P. So, that will become minus R T by P square, right. So, the tau T is basically minus 1 by V del V by del P, right. And so, V is equal to R T by P. So, you can write it minus P by R T into minus R T by P square, okay. This will cancel out, and minus will become plus, this is 1 by P, right. So, if the P is your 1 atmosphere, that is 10 power 5 Pascal, this will become 10 power minus 5, and the Pascal is per meter square, this will become meter square per Newton, right. Similarly, you can calculate for your isentropic compressibility also. So, this is the value that we are getting for air, okay. For liquid, your compressibility value is 10 to the power minus 10, okay. So, you can easily see that there is a order of like there are 5 order of difference between the liquid and the air. So, if we go by the previous expression, okay, this one, okay, because the tau is an important factor. So, 10 to the power minus 5 order is very it makes the difference how the density would be changing due to the application of the pressure, and that is why we say that the liquid, the air, the gases are compressible, but liquids are not compressible. Okay. Now, the last question is the compressibility is the property of the fluid. So, if the fluid is compressible, does it also mean that the flow is also compressible, right? So, that is something we will discuss in the next class. Remember, there is a difference between the fluid and the flow. Okay. So, there are some properties which are of the property of the fluid, for example, molecular viscosity, compressibility, these are the property of the fluid. But when the fluid flows, it may flow with a certain velocity, okay, and based on what is the condition of the flow, there may be some properties which will be varying. Okay. For example, how much turbulent the flow will be depends on what is the condition of the flow, not the fluid. Okay. So, the question is, when will we say the our flow is compressible? We have taken, okay, we are taking gas, okay, we are taking an ideal gas or air. So, we are expecting that because the flow it has got higher compressibility, it may become compressible, but at what condition we should say that it is compressible, the flow is compressible, right. So, we will discuss that in the next class. Thank you very much.